Hi, I am Muhammed Burak Kantar, and this is my YouTube video for my computer organization lecture, homework 3, and this is my school ID, as you can see. So in this homework, we have three different data types, data access types, which is matrix, stride, and linked list. So I just run three different Python files, which takes random instructions and calculates the miss rates for them in CENG204. So this is the solution I just got, so I will answer the questions according to that. So our first question is, how does block size affect each trace? So in our matrix, or when our block size is 4, I will just take every associative one. When our block size is 4, we have 0.25 miss rate. This is really low, really better. So when in block size 32, we have 0.03. So this is just better. So when we increase the block size, we have a better hit rate. In strides, on our block size 4, we have 100% miss rate. So just doesn't hit anything. I will explain it later why it just doesn't hit. And in block size 32, it's just the same. It just doesn't affect anything because the stride missing everything, doesn't take any instructions. So in linked list, we have, when we have 4 block size, we have 0.95 miss rate. So it's really bad. It just got 45 hits. And when our block size is 32, it just go to 0.82. So it's just better. It's approved, not approved. It just it's increased the hit rate. So when we increase the block size, it's just better on linked list. So that was the first question. On our second question, we will track how associativity affects. So on our matrix, when our associativity is 1, we have 0.25. On associativity 2, we have the same. On associativity 4, we have still the same. So this just doesn't affect anything, because it just doesn't affect anything according to our calculations. I'm trying to keep it short for the 5-minute video. On our stride, we have 100%, 100%. It just doesn't change anything, doesn't affect anything. On our linked list, we have 0.95, 50, and on the second associativity, 0.95, 40. So 0.0010 just affects, and maybe we can say improved. We cannot say improved. It's just so close to 0, but it just improved according to the miss rate. So if we maybe instruct 1 billion instruction, then it will be just 1 or 10. I just couldn't make the maths, but we could have said 10 instructions, so it just improved, we can say. So the other questions are, which trace benefits from most from larger blocks, and which I will explain it in the spatial and temporal locality. So which trace benefits most from larger blocks? Because matrix using satisfies spatial and temporal locality very well, because since it's matrix, when we have temporal locality, we can get the same index, and we can just check it. Just if we got the index, we got the last instruction, we can just use it again. So it just works properly on temporal. And on spatial, we can just say, if we get the index, we can get the side of it. So in matrix, that's so easy. So matrix satisfies both of that. So because of that, matrix trace benefits from larger blocks. Like for example, we have 32 kilobytes size. So if you get 8 words with 4 bytes each, don't how can I say, if you get 8 words which is 4 bytes every one, and we have 32 block size, okay, we will miss only the one. Only the first one is gonna be miss, and then the other 7 is gonna be hit, because we can satisfy temporal and spatial locality. So I think it should be temporal. No, it's spatial. I explained spatial locality, and for temporal, I'm checking my notes by the way because I'm confused a little bit. And the temporal locality satisfies because of the nested loops ensure that the same memory address is used. So okay, in matrix we use nested loops, so we can say same memory addresses are repeatedly coming to fill the matrix or take the instruction, so it just satisfies temporal locality too. And in the second question, in associativity, it's linked list, because since the addresses are random, the hit on the same cache index is high. Okay, since the addresses are random, we can hit the same index again and again. So if we hit the same index again and again, we can just use linked list, and we can just place them side by side. So we will not gonna be miss. We will not gonna get any miss. We will just take hits every time, because it's the linked list. We can place them side by side. So this is the temporal localities proper implementation, I think I can say. It's just better in linked list, but matrix is satisfied that too, so the matrix is gonna be better than the linked list, since it just satisfies spatial locality too. And then the sixth question is, no, the 5 is which trace is the most cache friendly. So it's matrix, because we can see the miss rate in here, like it's even less than 0.1. I'm sorry. So it's the matrix according to the solutions, and explain the results using spatial locality and temporal locality. I explained for matrix and linked list, and for the stride, why stride fails, because our stride is bigger than the, where's our stride is, I think 64 bytes in here, and it's just bigger than the cache, I think, and then since it's better than, it just never takes the instruction and it misses every time. And according to the temporal, I think I cannot answer temporal or spatial locality in here, because we cannot take any instructions. But I can tell it lacks temporal, since every address visited once during the linear traversal. So we just cannot get the same index again and again, so it's just pointless to according to temporal locality. So that was my homework. I tried to answer every question. Thank you for listening. Take care.